Hello ladies and gentlemen, welcome to the third laboratory in the fourth week. It's good to see you again. Today we're going to be going over some of those spatial statistical methods that we essentially covered within the lecture in quite a theoretical high-level way. And now we're going to actually work out how to calculate some of those statistical metrics using an R script. So you need to be able to download this R script and also the data required from the Blackboard website, set it up in a local directory on your machine, as it states here, and be able to run it. Essentially, I need you to be able to understand what's happening, so do run the code one line at a time, break it down, move the code around, and hopefully that will really kind of cement your understanding of the topic. So before we begin, let's just make sure that we're in the right directory. So this question did come up before, and I thought I'd just quickly cover it again. So this little one-liner that I've got here basically just says, can you find the path in which the current script that we're running is in? And I've just printed it here to the console, so you'll see that this directory path here is basically where I'm running the R script right now. And then what I do is I assign it to this variable called folder. So when I do that, it appears over here in the global environment. The folder name has appeared. And now I'm actually able to set this folder as the working directory, as we've done here. And if you if you look in the help menu, then you'll see that the set WD, so set working directory, or if you use get working directory, these are ways to either find the current working directory or to specify which working directory you actually want to be working in, as we have just done. So now hopefully if we go get working directory, that produces the path in which we are currently running the code. Okay, fantastic. So that's a little bit of housekeeping. Now let's move on to measures of spatial tendency that we discussed within the lecture. So obviously there are multiple ways in which we can calculate these different metrics. Here we're going to focus on calculating the mean center. So let's load data in, and the data that came with this laboratory is firstly the locations of Major League Baseball teams from the year 1900, so 120 years ago. And then secondly, it's the locations of Major League Baseball teams from the year 2000, so 20 years ago. So let's load those in. You can see that we have 8 observations in 1900 across 7 variables. So we have the ID number, we have, that's the ID number of the row essentially, and then we have the team name based on the city, and we then have the state, we have the latitude and longitude coordinates, and also we have an X and Y coordinate as well. So latitude and longitude coordinates, these are in decimal degrees, that's the unit in which they're measured. And then the X and Y coordinate will, I think that's probably in measured meters, but we're not using those today. So these are important differences that you need to get to grips with when you're working with different data types, because actually making sure that different layers that you import are in the right coordinate reference system in order for them to be overlaid is a perennial problem and something which you need to be able to know how to fix. But more on that another time, because what we want to do here today is to do some spatial distance measurements. So in the second data frame for the year 2000, we've got 30 observations, so many more teams by this year in the US and also in Canada. And it has the same number of rows as well. Okay, so how do we calculate the mean center? So essentially we want to find the average longitude and the average latitude coordinate in order to find that mean central location. So we can do that by taking the mean of the latitude and the longitude as we've done here, specifically for the 1900 year 1900 data set. And then also we can do the same where we take the mean latitude and the mean longitude for the year 2000 data set. And each time I've allocated them to a variable name. So the mean latitude 2000, the mean latitude 1900 or mean longitude 1900. And then I've printed them to the console. And here we've done the same with the mean latitude 2000 and the mean longitude 2000 and printed these to the console. And you can just see already, just by kind of looking at the numbers that's being printed, that there is quite significant difference in the actual location of the mean center between these two different time points, as we're going to get into as we move forward. So how do we plot this data? Well, we can plot it, just as a 2D plot, as we've shown here. It's not very intuitive. This isn't something that you could put in a paper. This isn't something I would encourage you to put in a report either for your work. But it does allow us to plot the points here for the year 2000 on a longitude and latitude coordinate reference system. So they are in abstract space. It's quite hard to work out where they really are. We can then actually overlay, because these previous points were for the year 2000, we can overlay the 1900 data locations for baseball teams, as you can see here, in the red triangle. So we've basically said that we have these additional arguments. So the PCH2 allows you to change the character type, and the COL, so color, basically allows you to change the color for the individual points, and that's why we're able to differentiate those two different time points here. We're also able to add the mean centers, so we need to change the data inputs to those mean values which we calculated, and we also wanted to change some of the other parameters so that we're able to now see exactly where the mean centers are. So in the year 1900, the mean center is over here, in the very center of the red triangles, as you would expect. And then by the year 2000, the mean center has moved out a little bit south, but also quite significantly westward, as these other baseball teams have been created. Okay, so that's one way to plot the data. There are better ways, so let's look at how we create those nicer maps. So in the previous labs, we looked at how we install external packages. And firstly, what we need to be able to do is to run this one line, which you only do once when you're installing on your machine. And that basically says, install the ggmap package for me. And it wants to update the package and restart R, so I clicked yes. Now it's basically saying that it needed to download some other packages in order to install this on my RStudio package, so that's fine. And then it's what we need to do is we need to load the library into the current workspace. So this just installed it on the machine, but then we need to say, actually, in this R session, we want that data package, so bring it into the current environment. And when we do that, it also loads in ggplot2, so we have plotted within this data package before in the first laboratory. And essentially, the GG part actually stands for the grammar of graphics. So you might say, why is it called ggplot2? But actually, it's got quite a logical name for why it's called that. And the actual script that you use in R has developed over many decades. So this is a fairly, well, it's a very well-known language within statistical computing circles. And increasingly now with the industry as well, as it's applied to many more things. So that's loading the data. Before we just manually calculated the different point locations, and we had them just within the value space in the global environment. But this time around, I want to create a single data set which combines all of our 1900 and year 2000 data into a single data frame. So what I've done here for BB19 is I basically said, create me a column called year and give it the number, the value, 1900. And then I've done the same for the year 2000 data. I said, create me a column and give it a year, the year 2000. And then what we want to do is we want to say, okay, now take our two individual data sets of different sizes, but the same number of columns, and just combine them vertically so that it creates one single large data frame. So now when I run this code here, what we've done is we've used the row bind function for the two data frames that we identified before. And it's created this one mega data frame called all data. So you'll see for the year 1900, we had 8 observations, and the year 2000, we had 30 observations. And when we then combine them together, we get 38 observations across the 8 different variables that we're interested in. So that's the data which we're going to plot. Now I want to create an actual data frame out of those mean data values, so the mean center values. Before we just specified them, as I mentioned, in the environment as individual values. Now what I'm doing here is I'm saying I could actually give me a vector called lon, so for the longitude, and a vector called lat for latitude, and a vector called year for the two different years where we have the mean values, and now stitch them all together to give me a data frame. And when we run this code just here, you can see that now we have the longitude, the latitude, and the year in a data frame, which allows us to actually give that data in an easier way to the function which we're going to use. So qmplot is a function which is part, I think is part of ggplot. Yes, it is. That's why we're using geompoint down here and facet wrap. So for any of you who get familiar with ggplot2, you'll start to recognize some of the function names. And what we're going to do is, in this first part, we're going to specify the data that we want to use, which is all data. Then we're going to specify the coordinate columns for the longitude and the latitude, as I've done here. And then I'm going to say, actually, can you color my data points red? And this time around, give me a map background, because last time it was really quite hard to make out the points that were just in an abstract space. Okay, and then we have this next function called facet wrap. Now, what does that do? Well, you'll remember that I specified which data were for 1900 and for 2000. And now what I'm saying is we want to have multiple maps based on the year category. Create multiple maps based on this nominal data column, and then place these different maps in one single column. So n is the number of columns. I want it to be one column, and I want it to be vertical. So when we run that, what we end up with is a map on the top for 1900 with our Major League Baseball team locations plotted. So you can see most of the major cities have teams. And then as we get down to the year 2000, you can start to see that we have many more teams, particularly out in the western parts of the US. And what we didn't do in this particular run was actually specify the mean central locations for those two different time periods. So the geom points just says, geom stands for geometry, hence it's spatial geometry data. And it's saying geom point, so this is point data that we're giving it. And it's actually taking the data that we placed into mean data, so the data frame that we made just up here. And we're saying the x and y latitude longitude coordinates are lon and lat. And then we want the shape to be something different so we can tell it apart. So let's pick a diamond. Let's fill the diamond with the yellow color so we can have some color variation in comparison to the red that's already there. And let's make it super big so we're able to look at the difference that's produced. And now when we look at 1900, we can see that the mean center back then for these different teams was just to the east of Pittsburgh in Pennsylvania. And then when we look at the year 2000, the mean centers moved quite dramatically, very much so to the west and also slightly to the south. And now it's just to the west of St. Louis, and you're able to see that we've got many more teams down in Florida, Texas, also out on the west coast, so San Diego, Los Angeles, San Francisco. So I think that that's a nice way to actually to visualize and start to understand the differences in the data in a single function. We're able to create this nice map, and actually we're able to look at where it sits relative to the United States. And you can do that with this function for anywhere in the world. So it's just pulling down the data map from I think probably from OpenStreetMap, from the application programming interface, the API. So if you just have any data for around the world, it will just pull down the relative map, which is nice and handy. So let's move on now into how we actually measure distance. So we covered in the lecture that we're able to measure distance in multiple ways. Let's start here by measuring the Euclidean distance. We can calculate the actual distance that the mean center moved explicitly, and we can do that using Pythagoras' theorem in order to get the straight line distance. I think one thing to note is that here we are just using decimal degrees. We're not actually using a linear reference system such as meters. So obviously if you were wanting to get that direct measurement, then that would probably make more sense to use a coordinate reference system that allowed you to explicitly measure that. Although, to be fair, you can actually use some conversion factor from the number of degrees to meters, but there are always issues with how how reliable some of these estimates are, because ultimately we're measuring distance on a globe which has been flattened, and that's why these types of inaccuracies always start to introduce themselves when you're doing particularly global spatial science, essentially. So a lot of the time in my own work, it's hard if you want to measure distance across lots of different countries. You need to make sure that your coordinate reference system is able to handle that, and you need to validate and check that it's actually doing what it's supposed to do. So anyway, let's have a go at trying to measure this distance. So the Euclidean distance takes the square root of the sum of squares of each coordinate's deviation. So here we are taking the sum of squares and taking the square root, as you can see. So let's run this, and the answer that we're going to get is approximately 13 decimal degrees when we round it. So that's the difference that the center mean has moved. I mentioned within the lecture that there's lots of different ways to measure distance. One of them is Manhattan distance. So the straight line distance is literally as the crow would fly. But basically, the Manhattan distance actually takes into account the fact that if you were, for example, in central Manhattan, then you wouldn't really be able to take the straight line distance. You would actually need to be able to navigate through the street network, which is going to be essentially at right angles. So I just have this small example here of the difference between the Euclidean distance, which is essentially a straight line. Or if you're going to take the Manhattan distance, you can't go direct, so you would need to take one of these other paths, essentially. So let's calculate the value that we get. The difference here is that we take the absolute value when we subtract the two different coordinate sets. So x1 minus x2 plus the absolute value for y1 minus y2. And what we get is 14.85, essentially, in decimal degrees as the Manhattan distance. So moving on, now we're interested in spatial measures of dispersion. there's multiple ways in which we can do this. Today we're just going to focus on measuring the standard different distance, as that's something which you're probably going to use quite regularly if you do go into spatial sciences for your career, and it's a nice metric to have. So let's calculate the standard distance for each baseball year. So this allows us to understand the absolute dispersion in each. And we get this value essentially by summing the square deviation from the mean in each coordinate, and then adding those sums together, and then dividing by the number of spatial objects and taking the square root. So you will remember that this is quite similar in how we calculated this to the standard deviation. So rather than doing it all in a big one-liner, I've broken it down into smaller chunks here. So what we're doing is we're taking the mean in the year 1900 for longitude from each of the longitude values. So we subtract them, and then we take the square root. So then we raise it to the power of 2, so we square it, and then we sum these values all together. And then we end up with an x19, an x value and a y value for the year 1900, which we have just down here. And then what we're able to do is we're able to add them together, divide them by the length, so the number of spatial objects that we have in the data set, and then take the square root. And then when we do that, we end up with this value down here for 1900, where the standard distance is about 6.8 degrees, decimal degrees. Okay, so now let's do the same for the year 2000. So what we need to do again is to get the sum square deviation from each coordinate to the mean center in each direction. So we're going to, again, we're going to subtract the x bar value, so the average longitude value here, from each longitude value that we have for the year 2000, and then we're going to square those values and sum them all together. That's how we get the x20 and the y20. And then what we're going to do is we're going to add them together, so that's the sum of squares, and then divide by the number of spatial objects that we have in the year 2000 data set. And then we take the square root in order to return it to the units of the original data. And then when we do that, we get an answer for the year 2000, which is 17 decimal degrees. So there's far greater dispersion as a consequence of there being many more points, but particularly those points being very geographically dispersed because of the shift of population, particularly to the western areas of the United States over the past 100 years. Okay, so that's the end of this particular part of the lab. There will be a new assignment which I will set for this week, which will be due the following week. If you do have any further questions, or if you have any queries about this particular part of this week's assignment, then just let me know, or obviously for this lab, and I'll look forward to hearing from you. So thank you very much for your time, and I'll speak to you all soon, I hope. Goodbye. Thank you.